Okay, today we get to start modern physics. This is going to be a wild ride. Today we'll be giving you an introduction to relativity. Pay close attention because everything you know is wrong. What we're going to be discussing over the next few days is going to be very counterintuitive, but really exciting. All right? You will no longer feel so comfortable watching science fiction after you have taken this class because we're going to blow away a lot of their assumptions. Okay, so today we're talking about Einstein's theory of special relativity. And I'll tell you what that theory is in just a moment. But in today's discussion, we're going to be focusing on two results of Einstein's special relativity. Two things that come. Once you assume Einstein's theory of special relativity, there's a bunch of weird stuff that comes along with it. And a couple consequences we're going to find today is that when a clock flies past you, it takes longer than a second between ticks, as measured by you. But somebody moving at the same speed of the clock will see the clock ticking at the correct rate. All right, this is known as time dilation. The other effect we're going to discuss today is the fact that when a meter stick flies past you, it is shorter than a meter, as measured by you. Now somebody running alongside the meter stick will measure the meter stick to be exactly 1 meter. This is what's known as length contraction. So watch for it. These two things are going to show up. But before we can come up with these consequences, we need to tell you what Einstein's theory of special relativity is. But before we do that, let's talk about a more familiar kind of relativity. Relativity, a theory of relativity, is basically just a theory that tells you how things that occur in different reference frames would appear. For example, imagine I have a spaceship flying by another spaceship. And I compare what I see watching on Earth as these two spaceships fly by to what is seen by somebody traveling in one of those spaceships. All right? So relativity, a theory of relativity, just basically says if I make measurements in the Earth reference frame about how these two spaceships are moving, what will the person in one of the spaceships perceive happening where they are at the center of their coordinates? In the Earth reference frame, I see both spaceships moving. In one of the spaceships reference frame, they are at rest, the Earth is moving backwards, and the other spaceship is moving relative to them, but at a slower velocity than the velocity we measure for that ship on Earth. And that's what relativity is. It's transferring physics knowledge from one reference frame to another reference frame. All right, in this class we are going to be using specifically what are known as inertial reference frames. An inertial reference frame, this is important, an inertial reference frame is one that's not accelerating. So if I have my two spaceships flying by the Earth, all right, and they're accelerating, neither of them is an inertial reference frame. But if they're both traveling at a constant velocity, then they are both inertial reference frames. All right? And this spaceship, if it's traveling at a constant velocity, it's an inertial reference frame. I can transform into that frame and see what happens relative to that frame. All right? So technically speaking, the Earth is not an inertial reference frame because we're moving around the sun and so forth. But the idea of an inertial reference frame is it's a reference frame in which if there's no force, there's no acceleration. If you're floating out in space and you drop your keys, they just float there, they don't fall, right? And if you were in an accelerating reference frame, you let go of your keys, you're going to see them moving backwards relative to you because you're being accelerated forwards. All right? So an inertial reference frame is one in which is not accelerating. So if I have two inertial reference frames, they will be moving at a constant velocity relative to one another. All right? Now, Galilean relativity is what we call classical relativity. So in classical relativity, if in the Earth reference frame, one spaceship is moving at velocity UA, and when we do relativity, we use U to represent the velocity of an object. All right? Talk about that in a minute. Let's say the other spaceship is traveling at some velocity UB. All right? Now, if I want to find out what's happening in the reference frame of spaceship A, what do they see? They're going to measure spaceship B to travel at a velocity, we call this UB prime, that's the velocity they see that spaceship traveling at. They see it traveling at the speed we see it traveling at minus the speed that spaceship A is traveling at. That's Galilean relativity, right? I just subtract off the velocity of the reference frame we're going into. All right, so Galilean relativity is relativity the way you would expect it to be. Turns out that it's wrong, though. But let's think about Galilean relativity for just a minute. All right? According to Galilean relativity, the idea is that the laws of physics should be the same in any inertial reference frame. So if I'm traveling on a train at a constant velocity and you're standing on the Earth, if to the extent that the Earth is a valid inertial reference frame, the train is one as well, because we're traveling at a constant velocity with respect to each other. So if I throw my keys up and then catch them while I'm on the train, they will go straight up and straight down, right? They will form a parabolic trajectory, right? But a degenerate one, right? The laws of physics, force equals mass times acceleration, right? They work in my train reference frame, and I can use those laws of physics to calculate how long it'll take for my keys to come back. Now for you standing on the ground, you see me going by. Now my keys have an x component in addition to a y component of velocity as they fly through the air. But the same laws of physics will tell you the trajectory of my keys and how long it will take for them to come back to my hand. All right? So the idea of relativity is that the laws of physics should be the same in every inertial reference frame. Okay, so some conventions. In Galilean relativity and in Einstein's special theory of relativity, we're going to need to define coordinate systems and come up with some conventions that help us go from one coordinate system to another. So I'm going to start with one frame. I'm going to call it the S frame. And the S frame is going to have a Cartesian coordinate system. I've got my x direction, my y direction, and my z direction. And I have some event that happens. An event that happens has a four-dimensional coordinate. It's got an x position, a y position, and a z position, but it's also got a time that it occurs. So I've got this point in space and time. We call this a space-time point. All right? So imagine I tell you in the S frame, some event happens at location x, y, z at some time t. All right? Now I want to find the space-time coordinate for that event in another reference frame that's moving relative to the S frame. We're going to call that frame the S prime frame. Here comes the S prime frame. It's moving with respect to the S frame. All right? So the primed frame moves with respect. Let's see it again. And notice the way I've drawn it, the x direction, the y direction, and the z direction are the same. They're in the same direction, but our origin is simply moving with time. Also notice that my origins pass through each other. All right? So just some conventions. I told you that if I wanted to discuss the velocity of some object moving in some reference frame, I'm going to use the variable u in relativity. We're going to reserve the variable v to be the velocity of the S prime frame origin as viewed by someone in the S frame. All right? And then we'll use u to represent the velocity of an object. So when I talk about v in relativity, I'm talking about the velocity of the primed frame relative to the unprimed frame. All right? Now we're going to define our coordinates such that the x, y, and z directions are the same for both coordinates. By convention, I'm going to define the x direction to be the direction that the primed frame is moving. So v is always in the x direction. And the origin of the two coordinate systems will overlap at time t equals 0. I'm just defining my coordinates that way just to make the math simple. So let's take a look at this again. What did we say? The velocity of the prime coordinate is in the x direction. The two origins overlap at time t equals 0. So time t equals 0 is now. All right? And then the x, y, and z directions are the same in the two coordinate systems. So those are the conventions that we're going to use to make our equations and our calculations simpler. Okay, so the Galilean transformations, what are the Galilean transformations? If I have some event that occurs at some position x, y, and z at some time t, where will the event occur in the primed frame? Well, the x, y, and z directions are the same, right? And the velocity is entirely along the x direction. So you would expect, right, if I go back up to my coordinate system and I look at this point up here, this space-time event, right? In the S prime frame, it's going to have the same y and z coordinates. It's only x that's going to be messed with. So y prime will be y, z prime is z, And the time that occurs should be the same, right? T prime is t. But because my coordinate systems are moving, all right, the position x prime is going to change with time, right? So if some event happens at location x at time t equals 0, it should also occur at the same location in the prime frame because their origins overlap at time t equals 0. But if something happens at a different time, the position is going to change. As the primed coordinate moves in the v direction, the event, right, in the primed frame is, if I have some object that's at rest in the unprimed frame, and the prime frame is moving this way, the object is moving backwards as measured by someone in the primed frame. All right? So if some event happens at some location x at some time t, in the primed frame it will occur at a different location. Okay? So these are the Galilean transformations. This is what classical physics gives us. They're fairly simple, but they are wrong, as Einstein is going to tell us in a minute. Okay, so everybody's happy with the Galilean transformations, but then in the late 1800s some weird stuff was happening. First of all, when you take Physics 220, if you take Physics 220, you'll learn about Maxwell's equations. They're the equations that describe electromagnetism. And it turns out you can manipulate Maxwell's equations and get a wave equation and realize, wow, light is just electromagnetism. Maxwell's equations describe light. But the wave equation that you get from Maxwell's equation, they're different from the classical wave equation. And it turns out they give you a wave whose velocity is the same in every inertial reference frame. Every inertial. All right? So they basically say that if you measure the speed of light in vacuum, you know, just kind of hanging out, hovering above the Earth, someone on a spaceship traveling past the Earth will measure the speed of light to be the same, the speed of light in vacuum. And that's kind of weird, right? Because if you were watching a water wave from the shore versus watching it in a speedboat, right? The speedboat's going to measure, in the speedboat you're going to measure a different velocity of the wave relative to you than someone on land. But Maxwell's equations implied that the speed would be the same for any observer in any inertial reference. It really bugged people, and they figured Maxwell's equations must be wrong, right? Because light must travel in some medium, and the correct inertial reference frame to measure the speed of light in should be one that's at rest with the medium. A couple guys by the name of Michelson and Morley set out to measure the velocity of this medium that light travels in relative to the Earth, right? The Earth's going around the sun's going around the center of the galaxy. It would be quite a coincidence if the medium that the light traveled in was at rest with respect to the Earth. They called this medium the ether, and they went to go measure the velocity of the ether. And that's what they used the Michelson-Morley interferometer for. As you recall from the last unit, in a Michelson-Morley interferometer, I take a beam of light, I split it with a beam splitter, reflect it off of two mirrors, and then bring the beams back together and mix them on the beam splitter. And by looking at the interference of the light coming out of here, you can measure kind of that path length versus that path length. If the entire apparatus is moving relative to the medium that light travels in, you expect to get a phase shift as you rotate your interferometer around. So they did these experiments trying to measure how fast the ether wind was moving, and they found that it's not. And eventually, Einstein came along and said, look, Maxwell's equations are right. The speed of light is the same in all inertial reference frames. And that's because there is no ether. Light is its own thing. So he comes up with his two postulates. This is all of special relativity in two postulates. The first one is the mathematical form of the laws of physics must be the same in every inertial reference frame. And number two is Maxwell's equations are right. The speed of light in vacuum is a constant, and it is the same constant in every inertial reference frame. All right? That seems pretty weird to me, right? That means that someone traveling by in a spaceship is going to measure the speed of light to be the same as someone not traveling on the spaceship and just floating up above the Earth, right? That's kind of weird. But the consequences of this are even weirder than these two seemingly benign postulates well, okay, I forgot what I was saying. Anyway, these are kind of weird postulates, but the results will be even weirder, as we're going to see. So, simple postulates, but with bizarre consequences. All right, first of all, imagine you have a single observer. Imagine this. And a train is going to drive by, and two bolts of lightning are going to strike the train at the same time. So here's just a thought experiment. Boom, these two events happen at the same time, but in different locations. All right? Now, one lightning bolt occurs here, one occurs here. To see this event, I have to wait until light gets from the event to my observer. They have to travel different distances, right? And so this observer is going to observe this lightning bolt before this one. Many people think this is what special relativity is all about, but it's not. This is a classical effect. We know about this, right? We know that it takes light time to reach your eye. So this single observer that measures these two lightning bolts, he sees one lightning bolt before the other, but then in his head he says, but I know how far away these are. I can subtract out the time it took light to reach my eye, and boy, I conclude they hit at the same time. So don't get confused by this. A lot of people think that relativity has to do with the fact that it takes a light time to reach your eye. This is a totally classical effect, has nothing to do with special relativity. And now for something completely different. So the single observer, by knowing how far away the events were, they can subtract out the effects of light travel time and conclude that the two lightning bolts actually occurred at the same time. All right? But just to make life simpler, when we do relativity, a lot of times what we do is we imagine a grid of observers. We have observers everywhere, and those observers only write down things that happen right in front of them. Okay? So we don't have to worry about the time it takes light to reach our eye. So each of these observers, they synchronize their watches. Maybe I send a pulse of light along and they use that to synchronize their watches, and then they watch what happens in front of them. So here comes the train in the Earth reference frame, the reference frame of my array of observers. The train comes along, boom, lightning strikes. And this observer says, I saw lightning strike here at some time. And this observer says, I saw lightning strike here at some time. And afterwards we gather up our notebooks and we say, these two events happened at the same time. And we don't have to worry about how long it takes light to reach our eyes. All right? So our Earth reference frame observers observe that the lightning bolts both struck at the same time. Now let's imagine what happens on the train. All right? Well, okay. In the Earth, let's stay in the Earth reference frame for a minute. In the Earth reference frame, both lightning bolts strike at the same time, but the person inside the train is moving. So as light travels from one lightning bolt to the other, that light must reach, the light from this bolt will reach their eye before the light from this bolt. All right, so imagine that the observers on the Earth, they see the person in the train. First, they look this way, and they see this lightning bolt occur, and then they turn their head and look this way and see that one. So they're going to see one occur before the other one, all right? But remember, that's a classical effect. It's, the time it takes light to travel to get to them, all right? So the people on the Earth, they observe that this person turns their head and sees this bolt, then they turn their head and see that bolt later. All right, but now let's see what happens in the reference frame of the person on the train, all right? So observers on the ground conclude that the observer on the train sees the light from the right bolt before they see it from the left bolt. But let's see what happens in the train. So in the train reference frame, we've got a bunch of observers, all right? They observe that both lightning bolts strike at the same time, but the speed of light is the same in this reference frame. So in this reference frame, it's not like the light coming from this bolt is going to travel faster than the light coming from this bolt, because the postulates, Einstein's two postulates of special relativity, one of which is the speed of light is the same in all inertial reference frames. So if these two lightning bolts strike at the same time, the light from them should reach the person on the train at the same time. That contradicts what the people in the Earth reference frame saw, where they saw this person look at this bolt and then look at that bolt. So either the observer on the train sees the beam of light, both beams of light at the same time, but that's not what the observers on the Earth determined. The other option is, in the train's reference frame, the lightning bolts didn't strike at the same time. So if we believe Einstein's postulates of relativity, including the fact that the speed of light is the same in all reference frames, we have to conclude that even though the lightning bolts struck at the same time in the Earth's reference frame, they did not strike at the same time in the train reference frame. First, this lightning bolt struck, and then this one struck. All right? So, first bizarre consequences of special relativity has to do with simultaneity. Things which happen simultaneously in one inertial reference frame do not have to occur simultaneously in a different inertial reference frame. Okay? Weird stuff, but real. Okay, now we're going to discuss time dilation. So imagine, if you will, I have a light bulb, a very, very short pulsed light bulb, and I'm going to use it to send light up to a mirror and then come back. And I'm going to measure. I'm on the train with a stopwatch, and I'm going to, okay, this is a hypothetical, right? Really, I can't do the stopwatch fast enough for a real beam of light, but I can do this in theory, okay? So this is what Einstein called a Gedanken experiment, a thought experiment. All right, so in my thought experiment, I'm going to have a flash of light that goes up to a mirror and then comes back, and I'm going to time the interval between the light leaving and the light coming back with a clock. Okay? Now, I measure how long it takes, boom, and I get my answer. But now let's see what somebody who's not on the train, an observer who's at rest with respect to the Earth, what are they going to measure? Well, in their reference frame, the light goes up from the clock, hits the mirror, and comes back down. But because the train is moving, the light has to travel further to go up to the mirror and then back down again. All right? But if the speed of light is the same in both reference frames, that means that the earthbound observer is going to measure a longer time between the light leaving and the light coming back, because the light had to travel a longer distance, but it travels at the same velocity. This is what's known as time dilation. All right? All right, when we talk about time dilation, the inertial frame in which the two events occur at the same place is known as the proper frame for the two events. So you measure the proper time between two events if you are in the reference frame in which the two events occur at the same place. Now, not all pairs of events have a proper frame. Okay, so it may happen that there's no proper frame for the time between two events. If two events occur in the same place separated by a time delta t proper, all right, then light can travel a distance which is c times that time divided by 2 and then back again. So the light in that time can travel a distance of that time times the speed of light, which means it can go out half that distance and make it back in that time. But in the frame of somebody who's moving at a speed v relative to the proper frame, so in the train example, those of us on the Earth, we were moving relative to the train, right? Relativity says it doesn't matter, you know, every inertial frame is equally good, so it makes just as much sense to talk about us moving relative to the train as it does to talk about the train moving relative to us. So in that example, we were moving at some velocity v relative to the proper train frame, and because of that, the light had to travel further than that distance L, which means there was a longer time between those two events. So the time between the two events in the moving frame is larger than the time in the proper frame. When I say moving frame, I mean moving relative to the proper frame, because every inertial reference frame is valid, right? We can think of one moving relative to the other, or vice versa. Okay, so conclusion, time is relative. When people say time is relative, this is what they're talking about. So here's something for you to think about. Two people in different inertial reference frame measure the time between two events. In which frame is the time interval between the two events? In which frame will the time interval between two events be the shortest? The one moving fastest with respect to the lab, the one moving slowest with respect to the lab, the one in which the events occur furthest apart, the one in which the events occur closest together. Depends on other information. You might want to pause the video and think about this before I spoil the surprise by giving the answer. Okay, are we ready for this? Turns out the one in which the events occur closest together, right? Moving fastest or slowest with respect to the lab doesn't matter. The lab is not special. Every inertial reference frame is equally important. All right, but remember, the frame in which the two events occur in the same place is the proper frame for the time between those two events. They measure the proper time, which is the shortest possible time you could measure between those two events. All right? Frames that move relative to the frame where we measure the proper time, they're going to measure a longer time, and the faster they move relative to the proper frame, the longer the time between the two events, all right? But also the further apart those two will occur. So in general, if two events occur further apart in some frame relative to another, the time between them will be longer. And if they occur closer together in a particular frame, they will occur closer together in time as well. All right, so let's do the mathematics. So in the proper frame, the frame that measures the proper time, light travel a distance L and back again. So the proper time between those two events is just 2L over C. So I have two events. I can use light as a clock to measure them. How far could light go, and then come back in the time between whatever those two events are. They could be me snapping my fingers twice or whatever. That's the proper time. All right, so the proper time is 2L over c. In a frame moving relative to the proper frame, the light has to travel further. It has to travel 2s over c in that time. Well, how long is s? Well, let's draw some triangles here. That distance right there is L. That doesn't change. This distance right here, right, the total distance right here is velocity times time, right? So this distance, half of my triangle, is half the velocity we're traveling times time, all right? So that means that s, the delta t is 2s over c, but s is just the square root of this length plus this length squared, all right? So if we then take this equation, right, we know everything in here except for delta t. We can solve this for delta t, and we find delta t squared is equal to this. Pulling that over, we can write L, right, if we bring the 4 over c squared in, I get this, and 4L squared over c squared, that's just 2L over c squared. That's just the proper time squared, all right? So once again, just doing algebra, we find that delta t, the time in the frame moving relative to the proper frame, is just the proper time divided by the square root of 1 minus v squared over c squared. We can also write this as the time dilated time, the time in a frame moving relative to the proper frame, is just gamma times the proper time, where gamma is 1 over the square root of 1 minus v squared over c squared. Now notice gamma, if v is equal to 0, if the two frames are the same, I get the same time because gamma goes to 1. But as v increases, this gets smaller, which means gamma gets bigger. Gamma will always be greater than or equal to 1. So as we move faster and faster, gamma gets bigger, and the time between the two events gets bigger. All right, so that's time dilation. Now, this is kind of bizarre, but it's not just made up. This isn't just a fairy tale. This isn't just some theory. This has been tested and verified many times. One of the first tests of special relativity was people making muons. Muons are these unstable particles. They're kind of like electrons, but they're not electrons, and they decay. You can make them in colliders, and they decay with an average time of about 2.2 times 10 to the minus 6 seconds. All right, 2.2 microseconds. But people did experiments where they made these muons, but they were traveling really fast, a really high fraction of the speed of light, and they found that they lived longer. Why? Because in their reference frame, they live on average 2.2 microseconds. But in the Earth reference frame, which is moving very quickly relative to the muons, that lifetime is time dilated. All right? So there was one of the first proofs. Since then, lots and lots of experiments have been done. Experiments have been done with particle accelerators where they move particles really fast, and they see that relativity has to be used to describe these things. Justin Petros in our department has a pulsed laser that he uses to rip electrons off of atoms and accelerate them really fast, near the speed of light. It turns out the dynamics of how those electrons move cannot be described with classical physics. You have to use relativity to get the correct results. Turns out electrons and atoms, when we study atoms and what colors of light they make, you get the wrong answer if you don't include relativity. Cosmic rays travel really fast, hit our atmosphere, do all kinds of fun things. Relativity is not just some quaint idea. You need it. It's absolutely necessary to get the right answers. So this is real stuff. I'm not just making this up. I say that because students all the time say, that doesn't make sense, this can't be right. No, classical physics can't be right because it does not match the experiments. Relativity does. Okay, so we discussed time dilation. Our next bizarre consequence of relativity is something called the twin paradox. All right? Well, no, sorry. Back up. The twin paradox is still about time dilation. I'm getting ahead of myself. So the twin paradox is a paradox that people presented to Einstein, and they said, look, relativity can't be right. Because imagine this scenario. Imagine I have two twins, two identical twins. We're going to call one of them Goslo and one of them Speedo. Goslo is going to stay on the Earth, while Speedo hops onto a spaceship, flies out near the speed of light a long ways away, and then turns around and comes back. All right? Now, which twin is going to be younger when they get back together? Which twin is going to be older when they get back together? All right? Now here's the paradox. All right? People said, Einstein, think about this. Speedo's flying out into space at some high velocity. So according to Goslo, he's going to see, okay, so Speedo's got a watch that's ticking on his arm, right? Goslo's going to look at that watch, and Goslo's going to say, well, look, I'm not in the proper reference frame to measure Speedo's watch. I'm in a moving reference frame, so I'm going to see a longer time between the ticks on his watch. Therefore, I'm going to perceive that his watch is running slower. His heart is beating slower. He is aging slower. So Goslo determines that Speedo is going to be younger than him when he returns. But now let's look at things from Speedo's reference frame. In Speedo's reference frame, it's Goslo that's moving fast. Goslo and the Earth are flying backwards relative to Speedo's spaceship. So Speedo is going to see Goslo's watch ticking slower. He's going to see Goslo's heart beating slower. He's going to see Goslo aging not as fast as him. But when they get back together and stop and shake hands, you know, whose point of view was right? Is Goslo going to be younger? Is Speedo going to be younger? And so they presented this paradox to Einstein and said, Einstein, your relativity can't work. All right, what's the answer? Well, it turns out the little twin who stayed home, Goslo, is going to be older. And the answer to this conundrum that Einstein gave them was, you can't use the time dilation equations in Speedo's reference frame because Speedo is not in an inertial reference frame. Speedo was traveling at some velocity, but to come back, he had to change reference frames. All right, and that messes up everything. Means he has to accelerate. And acceleration, when we talk about general relativity, we'll learn about what happens in acceleration. But funny stuff happens when you accelerate. So it turns out Goslo is the only person who is in an inertial reference frame, only his calculation is valid, and it turns out Speedo will be younger than Goslo after the journey. Okay, now we're going to talk about the second bizarre consequence of Einstein's special theory of relativity that we're going to talk about today, and that's length contraction. So now we're going to do another experiment. Imagine instead of sending Speedo out and back, we're just going to send Speedo on a one-way trip to planet X or Mars. I think that's Mars I put there. All right? So Speedo is going to travel from Earth to Mars. And Goslo is going to measure how long it takes, right? Goslo is going to have his telescope subtract out effects due to the time it takes light to reach his eye, and he's going to figure out how long it takes Speedo to get to Mars. All right? So he's traveling at some velocity, he's traveling some length, and that determines how long it takes to get there. But let's imagine what happens in Speedo's reference frame. In Speedo's reference frame, he's not moving, it's the Earth and Mars that are moving. All right? So Mars approaches him, Mars is some distance away, it approaches him at some velocity v, and therefore it takes a certain amount of time for him and Mars to come together. All right? Well, here's the problem. All right? Speedo sees Goslo moving backwards at some velocity, the same velocity that Goslo sees Speedo moving in the opposite direction, right? So if those two velocities are the same, here's the problem. Who measures the proper time for the one-way trip to planet X? Goslo or Speedo? How do we determine which is the proper frame to measure the proper time? It's the frame in which both events occur in the same place. So Goslo sees Speedo leave Earth, arrive at Mars. All right? Goslo sees the Earth passing him right here where he is. Sometime later, he sees Mars passing him right here where he is. So it's Speedo that measures the proper time for the two events. That means Goslo is going to measure a longer time, a time-dilated time between those two events. If it takes longer between those two events, but both Speedo and Goslo see the same velocity in the problem, that must mean that in Goslo's frame, the distance traveled is longer. All right, so this is length contraction. In Speedo's reference frame, all right, Speedo measures the proper time to travel a distance L at a velocity v. Goslo measures a time-dilated time, which means he measures a different time traveling at the same velocity. That means that Speedo must have traveled a different distance. All right? So if the two times are different, the two lengths have to be different. Now, I've labeled what Goslo measured L sub p, or the proper length. So Speedo measures the proper time because the two events occur in the same place in his reference frame. But the reference frame where you measure the proper length is the reference frame in which the thing that you are measuring is not moving. So we're measuring the distance between Earth and planet X. Earth and planet X are not moving in Goslo's reference frame, so therefore he measures the proper distance between the two. But in Speedo's reference frame, they're both moving, right? The two ends of that distance are moving, so Speedo measures a length contracted length for that distance. All right? Well, we know then from these two equations, the ratio of the times is just the ratio of the lengths, and we know that the time dilated time is just gamma times the proper time. All right, so that cancels out. All right, and we get 1 over gamma is equal to the ratio of the lengths. So we can solve that to find the length contracted length is 1 over gamma times the proper length. So what does that mean? If I have a meter stick, it's 1 meter long. If it travels past me near the speed of light, the length I will measure for that meter stick in my reference frame, as it moves by, I measure the location of its two ends at a particular moment in time, and I say, the two ends at this particular time, they're this far apart, it will be less than a meter because of time dilation. All right? So time dilation causes length contraction to occur. All right. Now, remember, the proper frame for time dilation is the one in which the two events occur at the same place. The proper frame for length contraction is the one in which the object isn't moving. So if I want to measure the proper time between two events, I do it in a frame where the two events occur in the same place. If I want to measure the proper length of an object, I want to measure it in a reference frame in which the object is not moving. Okay, the barn door paradox. Here's another paradox that people threw at Einstein. All right? So they said this. Unfortunately, I don't have some pretty pictures for you, but imagine this, if you will. Imagine I have a barn, and it's got a door at either end. And imagine I've got a pole, which is a little bit longer than the barn. Okay? So imagine I give the pole to a really fast runner. That runner runs through the barn. Okay? Because of length contraction, the pole gets shorter. And in my reference frame, the pole will fit entirely in the barn door. So imagine as the runner runs through, very quickly I have people on either door. They very quickly, boom, shut the doors and then open them again. So for one single moment, the doors were closed and the entire pole was inside the barn. Length contraction allows us to do that. But then the unhappy masses say to Einstein, they say, well, wait a minute. What about what happens in the runner's reference frame? The runner is in an inertial reference frame. They're running at a constant velocity. In their reference frame, it's the barn that gets shorter. So how could the pole be entirely in the barn at one time? How can we close both barn doors at the same time and catch the pole inside of there? Well, then Einstein comes back and says, okay, you might want to pause the video here. I'm about to spoil the punchline. You probably want to think about this for a while. Okay, are we back now? All right, so here's the answer. In relativity, two things that are simultaneous in one reference frame are not simultaneous in another inertial reference frame. So in the runner's perspective, in his reference frame, what happens is he's running with this pole. Right as the pole approaches the far door on the barn, that door closes and then opens. Then the runner proceeds through, and when the back of the pole reaches the back door, that door closes and then opens. All right? So the trick here is, in the runner's reference frame, the two doors don't close at the same time. And that is relativity. Good luck chewing on this one. It will haunt your nightmares from now on until you come to peace with relativity.